Alright, hi ladies and gentlemen. Today we're on our third day of this lesson 3-2. We've split it up into three pieces because it's important. There's a lot of information here. I can't imagine having gone through all of this in one day. Today we want to talk about using logarithms to solve word problems. So I have my calculator up. I'll probably be using it quite a bit today. Just wanted to remind you that when we use the term common logarithm, that means a log with a base of 10. And our calculator knows base 10 logic, which is really nice. So we can use our calculator's logarithm key to solve common logarithms. And usually, you will remember, if we mean a common logarithm, they don't put the little base down there. When you see the word log by itself, it's assumed that that is a common log or its base is 10. So let's take a look at this little problem that we have here. The percentage of adult height attained by a boy who is X years old can be modeled by f of x equals, and you can see the rule there, 29 plus 48.8 times the log of quantity x plus 1, where x represents the boy's age and f of x represents the percentage of his adult height. The question we have, approximately what percentage of his adult height has an 8-year-old boy acquired? Well, that means that we really want to know about this function when x is 8. So we're going to replace x with 8 in this. And according to the rule, it will be 29 plus 48.8 log of 8 plus 1, or 9. Alright, that's something that I can put into my calculator. It does understand. We'll put into our calculator 29 plus 48.8 log, and we might as well do the 8 plus 1 because we know that that's 9. And let's see what it tells us. The result that we get is 75.6 approximately. And this function is telling us what percentage of his adult height that 8-year-old has acquired. So the 8-year-old is about 76% of his adult height. For me, that was quite small if I had been a boy. I'm sure the girl formula is close to that too. The next one is one for you to try, of course. This time we want to know about a 10-year-old boy, and I'm sure that we'll find that that has gone up, but maybe not by as much as we'd expect. So we're going to put it back into our calculator, 29 plus 48.8 log, and this time it's 10 plus 1, or 11. You know, you can always ask your calculator to bring back the last thing that it had in its memory. I'm going to second and then enter, and it brings back that keystroke. So all I have to do is go back in here and change that 9 to an 11. And I don't have to retype, which is kind of a handy thing to remember. Yeah, based on that rule, we've gone up to 79.8, so we're at about 79.8% of adult height if we have a boy who's 10 years old. So we just used a logarithm to solve a word problem. Kind of interesting. Here's our next one. Oh, you know, it took me a long time before I realized that the Richter scale was exponential in its format. I don't know why I didn't know that, but I didn't until I started teaching this class. So we've got a little formula here about the intensity of an earthquake. It says the magnitude R on the Richter scale of an earthquake of intensity I. So I on top represents the intensity of the earthquake, is given by, and here's the formula, it's the log of the intensity of this earthquake over I sub O, which is the intensity of a barely felt or a zero level earthquake. The earthquake, it says, that destroyed San Francisco in 1906 was 10.83 times as intense as a zero level earthquake. What was its magnitude on the Richter scale? Well, I'm sure that we could probably answer that question without using the formula. However, R equals the log of, and it says you take the intensity of the quake that you're interested in, and this was 10 to the 8.3, and you divide it by the intensity of a 10 to the 0 earthquake. Well, you remember that 10 to the 0 is 1. So essentially what this is saying is that intensity will be the log of 10 to the 8.3. So we just have to figure out what the log of 10 to the 8.3 is. But we know that because this expression just means what power do I raise 10 to get 10 to the 8.3? Y'all, that's 8.3, and that's one of those silly properties that we had a couple of days ago. So the magnitude of this earthquake on the Richter scale would be 8.3, which is that's pretty strong. In fact, that kind of a quake would cause a lot of damage and loss of life. 8.3 on the Richter scale, depending, of course, on where it was. Let's take that same formula and see if we can apply it here. If an earthquake is 10,000 times as intense as a zero-level quake, that is, if I is 10,000 times I to the O, what is its magnitude on the Richter scale? Well, here's what the formula says. It will be the log of the 10,000 times as intense, so we're 10,000 I sub O over I sub O. And anybody who knows their fractions knows that that cancels out. So really we're asking you for the log of 10,000. Or you would think to yourself, what power of 10, or what power do I need to raise 10 to get 10,000? What power of 10 does it take to get to 10,000? Right, because the common log has its base of 10, so 10 to the nth would give us 10,000. Well, you can figure that out really easily, and some of you probably already have, but 10 to the first is that, 10 to the second is that, 10 to the third is that, and you can see the power is the same as the number of zeros. So the log base 10 of 10,000 must be 4, has 4 zeros, so it's on the Richter scale, a magnitude 4 earthquake, 10,000 times as intense as a zero-level quake. That is, even that, for a Richter scale 4 is a strong earthquake. So, and I've always been grateful that I did not live in a place where those kinds of things happen. Although I'm pretty sure I felt an earthquake one time that happened in Ohio. All right, let's move on and see if we can finish up this little lesson. Our natural logarithms have base e, as you'll remember. The domain information for natural logs is the same as for any other logarithm. That is, domain has to be bigger than 0, and it can go to infinity. The properties that arise or that apply for any base logarithm, they also apply to natural logs. So anything that we know about logarithms also apply to natural logs. So here's a little problem that has a base E situation. When the outside air temp is anywhere from 72 degrees to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. You guys, that's why we hear about babies who die, because they are left in cars. That is a humongous gain in temperature. The function f of x equals 13.4 times the natural log of x minus 11.6 models the temperature increase in degrees Fahrenheit after x minutes. Use the function to find the increase in temperature to the nearest degree after 15 minutes and then after 30. So we're going to do f of 15. And according to the rule, that will be 13.4 times the natural log of 15 minus 11.6. Let's come over to the calculator here. 13.4 times the natural log this time of 15 minus 11.6. And according to the calculator, that means after 15 minutes, that temperature has gone up about 24.7 degrees. Okay, that's quite an increase after 15 minutes. After 30 minutes, so being in an enclosed car for 30 minutes, when it's this warm outside, 72 to 96, 72 seems relatively we'd think that that's pretty safe. But 30 minutes being in an enclosed car at that temperature, according to this rule, let's see how far that temperature would increase. We're going to second and enter again. We're going to back through this until we get to the 15, and we're going to change it to a 30. That's such a handy trick. Yeah, in 30 minutes that temperature has gone up to around 34 degrees. And if you think about that, if you started at 72 degrees and you've gone up to 34 degrees, you're already over 100. That heat builds so quickly in an enclosed vehicle. So let that be a lesson to us, I guess, today. That's what we've learned, that we don't want to leave our pets or our babies in cars that are closed in warm weather. So that's our lesson for today. We looked at 3 little applications where logarithms were used to solve problems. We hope that you'll get right out there and get on that trig